Hello, and welcome to lesson 1.03, Classification Matter. This is a screencast, and I am Mrs. Willie. Let's get started. Matter is anything that has a mass and a volume. We classify matter using three factors. The first, the type of particle the sample is made of. The second, the composition of the sample, constant or variable, and I will get into a better explanation of what constant and variable composition are as I go throughout the screencast, and the separation method required to separate the sample. Matter is anything that has a mass and a volume. We classify matter using the following factors. First, the type of particle the sample is made of. Second, the composition of the sample, which we're going to focus on constant composition or variable composition, both of which I will describe further when we go on to slides that are coming up in this screencast. The separation, and lastly, the separation method required to separate the sample. So let's start with the types of particles, that first bullet point. Type of particles could be an atom. Most of you are familiar with the atom. Atoms are classified as metals, nonmetals, or metalloids. In this particular example diagram I've given you is a monatomic atom, which means the atoms are by themselves. So if I were to draw another, let's say, copper atom right next to this one, they would not be bonded. They would just be free-floating atoms, and those would be considered monatomic atoms. And they can be, again, metals, nonmetals, or metalloids. Then you have a particle called the ion. Ions are monatomic atoms that have a charge, which means they have an unequal distribution of the protons and the electrons. You can have a cation, which is a positively charged particle, which means it has a greater number of protons inside the nucleus as compared to the electrons in the electron cloud. And it's easy to remember the cation because of the T in the word. That is the positive charge. Their other type of ion is the anion. Anions have a negative charge, which means that there are more electrons in the electron cloud than there are protons in the nucleus. When we're thinking about ions, we are thinking about free-floating ions. So if there was another one of these, it would be free-floating. Another one of these anions, it would be free-floating. They would not be bound together. I'm making this distinction because we're about to go to formula unit. But I want to talk about that constant versus variable composition. So this would have a constant composition, a sample of matter of this particular monatomic element would have atoms that are the same. So they would look the same. It would all be the same throughout. When we look at the ion, we'll go back to the ions that we talked about. They too would have constant composition because a sample of these cations would be the same element, the same charged particles, and so all of the particles inside that sample would be the same. So they would have a constant composition. A sample of these anions would have a constant composition as well because all of those charged anions, those charged particles, are the same throughout. When we get to a formula unit, now that we are there, this is when you have a cation and an anion that attract to one another. The attraction there is called the Coulombic force. It is okay if you don't know that force and you don't need to memorize it yet. But in a formula unit, the positive cation attracts the negative anion, and they create an overall charge of neutral, and they would be considered a variable composition because you have two different types of ions here. You have a cation and an anion. Those are elements that are charged particles, two different elements that have two different charges. So they would have a variable composition. Then we have what is called a molecule. Molecules are made up of only non-metal elements. In this first example, you have a molecule of two different non-metals. So this would have a variable composition. And in the second example, you have what we call a diatomic molecule, but it's made up of the same type of atom. So you have two of the same type of atom here. So this molecule would have a constant composition, whereas this top molecule would have a variable composition. So let's move on to the what a pure substance is. A pure substance has a constant composition throughout. So kind of where I gave you examples of constant and variable composition, I'm going to talk more on that on this slide as well. So pure substances can be classified into two subcategories. The first being elements. Elements then have two subclassifications, a monatomic atom and a diatomic molecule. There are only 7 elements on the periodic table that create diatomic molecules. We call them the 7 twins because they're never found in nature alone. They are bound to themselves or other atoms of a different element. But we would classify them as an element because they are the same. They're of constant composition. And so if you would please take note that hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all create diatomic molecules and are known as the diatomic molecules. The little 2 that you are seeing here is called a subscript. This indicates that there are 2 of those atoms bound together. So whenever you see that, you know that there are 2 atoms in that molecule. In this case, they are the same atom. You also have what is called a compound. Compounds have variable composition if we're talking about one particle of that compound. But when we put the sample of all of those together, so if I have a sample of this cation and anion, this formula unit together, and I have more than one of those formula units, they are the same formula unit throughout. So they would have a constant composition, which is why they are classified as a pure substance and not as a mixture. Compounds can also be molecules, and like I just mentioned, the particle of this molecule has a variable composition, but if I were to make up a whole sample of those molecules, they would be the same throughout that entire sample. So the sample has a constant composition and then is classified as a pure substance, even though the particle itself is variable. So again, in compounds, the particles themselves are variable, but a sample of that compound has a constant composition and therefore is a pure substance. So an example of this would be table salt that you use at your house that does not have iodine in it, just pure table salt, would be classified as a pure substance because all of the formula unit particles throughout that table salt sample are the same. So we would say that that has a constant composition in the sample and would classify that as a pure substance. So you find pure substance on the periodic table. Hopefully we've all seen the periodic table before. We utilize the grade 8 science periodic table that you used on your grade 8 science STAR test in our class as well, just to keep that consistent with what you've hopefully seen in the past. All chemical symbols of elements are written starting with a capital letter. So if I see a formula and it has a capital letter, then I know that that is one element by itself. Some elements have a capital letter followed by a lowercase element like chlorine. But we know that if I'm writing a compound that has, say, boron and chlorine in it, that this has two different elements because of the uppercase capitalized letters in that formula. So that indicates that there are two different elements in that formula. So compounds contain only one type of formula unit or molecule. And so back to my table salt example, you would write the formula for that in ACl. I would know that that is made up of two different elements because I have two uppercase letters within that formula. And then molecules that are made of two or more different atoms because we are talking about compounds here. Carbon dioxide, remember again that subscript means that there are two oxygens inside that formula, is made of two different elements because I have two uppercase letters in that formula. So let's talk about the chemical formula that's used to represent the element or the compound. So going back to monatomic versus diatomic, the symbol for gold is AU. So if I have just the symbol there, then that means it is a sample that is made up of the monatomic element gold. So not just one simple atom, but many atoms. But all of those atoms are gold atoms. Or they can be diatomic. So this sample would have many hydrogen diatomic molecules, but they would all be considered the same. So it would have a pure substance classification. Same over here for NaCl, and water is an example that you've seen before. So that brings us to the states of matter. So we just talked about all of the different types of particles and the difference between an element and a compound, really getting into constant versus variable composition. But I want to bring you back and have you remember kind of the states of matter, because all of those can be found within different states of matter, and how we draw them in a particle diagram depends on the state of matter that they are in. So you've probably learned that there are 4 subcategories of naturally occurring matter. We're only going to focus on 3 in this class right now and for this screencast, which are solid, liquid, and gas. So solids are tightly packed particles. They have a definite shape and volume. In your mind, visualize what a solid looks like. So envision a piece of solid aluminum, like your aluminum soda can that you drink out of. They have strong interparticular forces. We'll get into what that means. Interparticular means between each particle, and they are not compressible. Think about that aluminum can that you cannot compress the aluminum. You can compress the air inside the can, but you cannot compress the can itself. Liquid are freer flowing particles. They have an indefinite shape. They depend on their container. So if I'm thinking about liquid water, the water that I pour into my glass the shape that it makes is going to depend on the type of glass that I'm using. They have weaker interparticular forces, so the force between the water molecules themselves are weaker than those that are found in solids, and they as well are not compressible. You cannot compress liquid. Gases are free-floating particles. They have an indefinite shape. They depend on their container. So think about this as if I'm thinking about pure oxygen in the air or a pure oxygen tank that somebody is utilizing. The oxygen and those molecules inside that tank fill the space inside that tank. So the shape of those particles depends on the container itself. They have the weakest interparticular forces of the three states that we are discussing right now. So the forces between those particles are weak, which is why they can take the shape of their container, and they are compressible. So notice that is different from the last two. That is what makes gases unique, which leads us to the kinetic molecular theory. So gases are unique in that the forces between them are very weak, and the distance between the particles is very large. So the volume of the particle itself can be assumed to be zero. So they take the shape and the volume of the gas particles are entirely determined by their container. This is the postulate that explains why gases are compressible and can be moved from container to container very easily without changing the amount of matter present. The second postulate describes the kinetic energy of gas particles. They are in constant motion, so they have high kinetic energy. And since those forces between the particles are very weak, they collide with each other and the walls of the container, causing pressure. So it is the gas particles themselves that are causing the pressure inside of the container with their collisions. Postulate number 3, or the third postulate, they are assumed to exert no forces on each other. We know that in reality there's attraction and collision that are occurring, and these interparticular forces will be described later on, but in KMT we are in an ideal world that says that the particles do not exert forces on one another and this can go back to the fact that those forces are very weak between the particles. Finally, the average kinetic energy of the gas particles is directly proportional to the Kelvin temperature of the gas. The Kelvin scale is something you may not have heard of, and we will get into later on, but I do want you to think about just temperature and Fahrenheit temperature or Celsius temperature. As the temperature goes up, more kinetic energy is added and gas particles move faster, whereas as the temperature goes down, less kinetic energy and gas particles move slower. But in comparison to the other states of matter, solids, and liquids, gas particles have more kinetic energy and are faster due to the amount of their kinetic energy. So some example of particle diagrams that you could have to analyze or draw yourself look like this. In the first one, you have a solid. They have vibrational motion and appear to be tightly packed together, but not touching. In the second image, you have liquid. So notice they're spread a little further apart, but still their container is what's giving the volume. They fill the volume of their container. So they are not as free floating as what you see in the gas particle diagram. They have more kinetic energy than the solids, and then you get to gas particles, and notice the gas particles here are filling up the volume of their container, and notice there's a lot of kinetic energy, so these particles are moving faster than the others. And then we have a state signifier, or that you will see, that is aqueous. Aqueous is not a pure substance, so these first three, solids, liquids, and gases, are pure substances, whereas the aqueous state signifier is a mixture. It is a mixture of water and whatever other particle is in there. In this case, this is a formula unit because you have calcium hydroxide where you have a metal with nonmetals. So it is calcium hydroxide mixed with water molecules. And so when you see the aqueous designation, you have to know that that is with water, and it is a mixture, not a pure substance. Which leads us to mixtures. Getting back to the second bullet point we had from the very beginning is mixtures have variable composition, and they are physically mixed together. Having a variable composition in this case means two or more types of particles, not two or more types of atoms or ions. Do not confuse those. And they can be classified into two subcategories, a homogeneous mixture and a heterogeneous mixture. So remember your prefixes, meaning same or constant, and then variable. Homogeneous mixtures can also be called solution, and the composition here is uniform. So if I'm looking at the particle diagram or I'm looking at the sample itself, I cannot tell a difference between the particles inside it. So in this case, we have cations and anions and water molecules, but notice they are drawn in a way so that it would be that the water molecules and the cations and the anions are evenly distributed throughout the substance, throughout the sample. So we would not be able to tell those apart if we were looking at them. So this is what happens in salt water. The sodium cation is separated from the chlorine anion by the water molecules. And just think, when you look at salt water that you mix in your house, you cannot see the salt and the water once it has dissociated, and so it would have a constant or uniform composition. Heterogeneous mixture is not uniform. So when I'm drawing that particle diagram, I would have distinct layers. In this case, this would be like oil and water. So I would have a layer of oil that is less dense floating on top of a more dense liquid water layer. We would assume that both of these are liquids because they are not taking the full shape of the beaker, and they are not coming out of the beaker like a gas sample would be. So same over here, I can assume that this homogeneous mixture is a liquid because there are no particles coming outside of the beaker, and they are far enough apart that they would not be considered solids. Remember, those were very tightly packed. These are a little farther apart. So there are kind of different types of solutions when we're thinking of this as states of matter. So in this particle diagram, you have a solution that is gas particles because they are taking up their entire container. And I know that it is a solution or a homogeneous mixture because the composition is constant. It's pretty even, uniform throughout. They don't have those distinct layers that I spoke about in the last slide. And so, but solutions don't have to be gaseous. They can be liquid or they can be solid. When we're talking about solid solutions or solid homogeneous mixtures, we utilize the term alloy. Some of you may have heard this term before, and there are different types of alloys that we're going to get into later on. But right now you just need to know that a solid solution or homogeneous mixture is called a alloy, and it is made up of metals. So I have two different types of monatomic metals inside this mixture, tightly packed together and of uniform composition. They're spread pretty evenly throughout. It's not like I have all of the smaller blue particles in one layer and the larger red particles, atoms, in their own distinct layer. It's pretty evenly or uniformly distributed throughout the sample. You now have heterogeneous mixtures. So heterogeneous mixtures have layers because of different components of the mixture having different densities, or because they are insoluble. They do not dissolve in each other. They can have components of more than one state of matter or the same state of matter. So two subcategories of heterogeneous mixtures are colloids and suspensions. Colloids are solutions that have particle sizes large enough that they hang around. And I know this is kind of tricky because we said the word solution is a homogeneous mixture, but a colloid is actually a heterogeneous mixture. The reason why they're using the term solution there is because it has a uniform distribution, but the particles within that colloid have different densities. They're just closer together. So an example of a colloid would be fog or hand lotion or dust in the air. They stay suspended in an even or uniform distribution, but you can see the particles sometimes when we're thinking about dust in the air, but you couldn't see different types of dust particles. You would not be able to distinguish that. You would just see that general haze in the air. Then you have what is called a suspension. Suspensions are heterogeneous mixtures that contain particles that when you mix them, stirring or shaking, the particles become uniform, and then they settle into those different layers. So over time, they would settle into those layers. So I would have a suspension where I could see different particles inside of it. I shake it up, and then it would settle over time. So an example of this could be mud, where I have mud inside of the water. I shake it up, and that mud, I cannot tell two distinct layers, but over time the mud, the solid dirt particles would settle on the bottom, with the water, less dense water would be on the top layer, but there would be two distinct layers in my particle diagram. So you can classify solutions using what is called the tendal effect. Using the particle size inside of the mixture, you can classify it as a homogeneous solution or a heterogeneous mixture. So the tendal effect is when they take a laser and they shoot it through your sample. So in our first example right here, in a solution or a homogeneous mixture, the solute, which is the particle that is being dissolved, is smaller than 1 nanometer in diameter. So remember, uniform composition, you cannot see those particles, and they're evenly distributed. So when I shoot that laser through, it stops. The laser looks like it's coming in, and then it's floating through, and then it will come out the other side. In a colloid, you have what is called a positive tyndall effect. When the laser shoots through that uniform composition, because the particles are 1 to 1,000 nanometers in diameter, the solute particles that are inside, are so small that when you put that laser through, then it actually looks like the laser, you can see the line going through the entire sample, and that's what is a positive Tyndall effect. A suspension has particles that are larger than 1,000 nanometers in diameter, and they do not show the Tyndall effect when it has settled over time. Whereas if I shake it, then it will show the Tyndall effect, like the example from right here. But in this one, the solute particles that are so large have a greater density and have settled to the bottom, so it does not show the Tyndall effect. The filtration, I'll kind of talk about on the next slide what that means. So that last bullet point that we discussed is separation technique. All of these separation techniques would allow us to separate mixtures because they are physical separation techniques. So in our first separation technique, you would have filtration. Some of you have seen this in science lab. When I think about this, it's putting a piece of filter paper into a funnel. I pour my solution through it, and because of the different densities in that mixture, the solid and particle size, the solid particles will stay inside the filter, whereas the liquid particles will go through into whatever is at the bottom. In this example, it would be kind of what you've seen in the lab, whereas may have used what is called a sieve when you were looking for gold as a child. This allows different size to solid particles to fall through. You have evaporation. So this piece of equipment is called a hot plate. On that hot plate, you have what is called a beaker. Inside that beaker, you have a solution. When you evaporate or boil off the liquid portion of that solution, then any denser particles will then settle at the bottom. So again, going back to our salt water example that we've been using throughout, the solid formula units come back together from their ion state when they were in solution, and then you can see the solid salt on the bottom, and the liquid has been evaporated and gone from liquid to gaseous particles that are now taking the container, right? So the room. You have what is called distillation, which most of you have not seen a distillation apparatus before. In a distillation apparatus, you have what is called a round bottom flask that is connected to a distillation condenser tube. In that condenser tube, so right here, these tubes are connected to the cold water, and then you can see this blue area on the outside has cold water, and then you have this thin glass tube that is going through the middle where the water cannot come into contact with what's inside that glass tube. And then you have some sort of collection device over here. So I can put my solution inside the round bottom flask, put a Bunsen burner or a hot plate, apply some sort of heat to cause the liquid to go from a liquid to a gas. Those particles then go up the tubing and then come down. They then recondense as they go through the cold water condenser tube. So they go back from a gas to a liquid, and you would collect the different portions based off of boiling points. Then you have what is called chromatography. Chromatography is where and there are many different types of chromatography. Our example here is called paper chromatography. It is when different components of that solution move through a solid, in this case paper, It could be a liquid. We'll just focus on the solid for right now at different rates. Based off of those interparticular forces that we talked about. And so, like if I'm going up these, not all of these visible colors that you are seeing in that chromatography paper will go the same distance. They will travel farther based off of the size of those components, those different compounds that are inside the solution, the mixture. Then you have centrifuge. A centrifuge is a device that allows you to spin samples at a high speed, and it will separate them based off of density. So when you spin them based off of the density, the higher density will fall towards the bottom of a centrifuge tube, which is conical. It looks like this. So the higher density will go down to the bottom. The lower density would be on the top, and then you could pour off and keep whatever is on that top layer and put it into another container, and then work with what is on the bottom, the larger density. This could be liquids of different densities, so I want to separate two liquids, or it could be I want to separate the liquid from the solid, and I wanted to save both of those without having to evaporate that off. I want to keep that top part, so I would use a centrifuge to do that. So lastly, this is what is called a flowchart or a web diagram. So you can see I can classify matter as a pure substance or a mixture. Under pure substances, I can have an element or a compound. Those elements can be monatomic or diatomic. Compounds can be formula units or molecules. If I'm looking under mixtures, I have two types of mixtures, homogeneous and heterogeneous. Homogeneous mixtures are also called solutions. They can be solids, liquids, or gases. A solid homogeneous solution is called an alloy. And then a heterogeneous solution has two subcategories, a colloid or a suspension. And that is all for our screencast. Thank you for staying with me, and I hope to see you again.